All right, so let's now get started. Sorry, let me just move the slides. It should be here. Okay, good. All right, so let's discuss something actually very quickly. So we got one class today, and also the final class will be next Monday, which will be December 1st. And then I know that Wednesday will be your study day, and then our exam will be on the 17th, which will be like a Wednesday, right? So that's the kind of the schedule. I think in between the study day and also the exam, I think we can do two things. Number one, I would like to have a makeup class because remember I canceled one class before, so I want to make it up. So we can choose maybe a time that kind of work for maybe at least many of you who can come in person. I'm going to record a lecture, of course, just in case you really cannot make it. And then I would suggest, in addition to the makeup class, we got also at least one review session, just to see which day you might prefer. We can go over your questions, and then I'll talk about other things. Okay? I'm gonna set up survey on the e-class, but I want to have some idea, like which day you guys might in general prefer. So give me some quick feedback. Any preference? Let's start with the makeup, maybe a makeup lecture. I think that one should really happen first before the review session, right? Any day you prefer? Let's say sometime after the study day, maybe around this week, maybe? Or you prefer earlier?
Like anytime after the 7th.
For you, it's anytime after the 7th, right? Oh, you're talking about this week, basically, right? Guys, are you okay with this week, maybe? Okay. Any day you would prefer?
I like Wednesday.
You like Wednesday? Okay. Anyone else? Wednesday sounds okay, right? Okay, how about this? What I would do is I'm going to, I'll try to make this whole week as option. You guys can choose, okay? Any time you would prefer. So I'll try to maybe fit in maybe both the makeup class and also the review session, right? What time would you prefer? You prefer morning, afternoon?
In person or online?
Huh?
Is it in person or online?
I will, do you guys really prefer online or in person? What does it matter?
Like the timing matters to me.
Yeah, so I think, do you have any preferred time?
Like if it's in person, I'm fine with mornings, but if it's online, I prefer afternoons.
So you're saying in person morning will be okay, right? For you. No, it's okay. I'm just 1 to 3, right? Because you guys are basically the people who come to class, right? So I value opinion more. That's why I'm asking here, right? Sarah actually prefer, I think in person will be the best, really, we can interact, you can even stop me after the makeup class or review session. Morning?
I'm okay with noon. I don't want to be there.
Like noon time, not morning.
Yeah.
Oh, really? Oh, when you said morning, I was thinking about 7 a.m.
No, she meant 11, 12.
Yeah, 11, 12.
Okay, how about 11 a.m.?
Yeah.
Sure.
11 a.m. sounds good for everybody? How about this? I'll make the 11 a.m., 12 noon-ish for every day. You choose the one you want, okay? And then we're gonna make maybe at least one makeup class only one, okay? Yeah?
Will we be covering new topics during the makeup lecture?
We have to cover some new topic, that's the point. So, but I'll make it very self-contained and I'll tell you tell you everything you will need to know, just one lecture, okay? Okay, good. Okay, so what I would do is I'm gonna choose this week over here, and then I'm going to choose, because it's gonna be in person, I think that'll be the best for everybody. That can also urge me to come, so I will take it more seriously, right? Of course, I always take it seriously, but just say in person will be better. So I'll try to find maybe 11 a.m., 12 noon-ish, okay? Okay, sounds good. It's good for everybody, right? Good. Okay, so that's about it. And then, so today, let's skip the recap. Okay, so you guys can definitely start going over the material for the exam. It's gonna be cumulative. You can assume that anything we kind of cover in the lecture, in the tutorial, in the assignments may be covered in the exam. Okay, I can give you guys maybe more tips because I haven't really started designing the exam just yet. I might be able to give you guys a little bit more tips, maybe towards the end. Maybe not now. I'm not lying. I haven't really got the exam just yet. Okay. Okay, so we will talk about it. Okay, I'll keep you guys posted. So today, one topic. We're going to talk about something called topological sort. It's a very interesting topic, and we're going to do a little bit, it's more like a specialized graph we're dealing with. is called DAG. We'll get to it. And then we'll try to look at its implementation in Java. I'll give you some Java code. It's basically almost working. So for those of you who might be interested, you can also feel free to go back to your assignment number 1 or 2 and try to see if you can implement it. Okay, and then we're going to talk about do some exercises together, do tracing, and then I'll show you one interesting application about topological sort. Okay, let's just do some general background. Okay, so you got the slides already, but let me just write something here on the notes as well. Okay, right here. Okay, so just to start with, we are talking about a particular graph, which is called DAG, D-A-G. That simply stands for, well, you can see that here, directed acyclic graph. That means whenever you got any edge, it has to have a direction. So if I got 2 vertices, V and U, and it must have some arrow. Okay? And now we don't talk about weights anymore. Okay? It's not like a dijkstra, right? So we're not talking about weight, just direction. Okay? It is always directed. And also there's no cycle. Okay? There is one exercise I want you to do, very simple to do. Just look it up, right? Because you have no data sheets for the exam. Now, some exercise for you to find out. Given that DAG simply means something that's directed and also acyclic, how do you compare DAG versus a tree? Okay, very simple. Basically, go with this definition for DAG and go back to the definition for tree and try to compare them. They are not exactly the same. Okay, that's something you can easily do. Okay, I'll leave that to you. And the DAG over here, the arrow that we are having, usually will indicate certain dependency. Okay, so that's kind of it's a very important. Whenever you draw some arrow, you have to know which way the arrow should really go. We'll see example about how you should really draw the arrow. If you draw the arrow in the wrong way, then it's not going to work. Okay, so in the slides, I gave you some typical example. The one I'm going to draw right away, very soon, is something about prerequisite. For example, you must take 2101 before you can take 3101. That's kind of like a dependency, right? One thing cannot really happen until the prerequisite happened first. Okay, so there's a dependency there about the timing for the occurrence. So prerequisite is 1. Or for example, if you go back to 2030, where we talk about inheritance, whenever you say class A extends class B, in that way, there's also direction there, like a child extends parents. There's also some kind of dependency. Another one is about if you got maybe certain constraint about scheduling of tasks. For example, certain resources must be allocated before you can request for that, right? There's also some order that must be satisfied. And the last one there is something I would like to give you an example, a concrete example as well, to see how we can do something called topological sort on the DAG, right? So whenever you got, let's say, some specification of the variable assignments you want to achieve, but how can you schedule the order exactly how the assignment should be done? That's something I will show to you as well, right? Just want to list the bullet point one here. There are many practical applications you can use for topological sort. Any situation where you got dependency that exists between different events or different nodes, you can most likely can use a DAG and also topological sort. Okay, we'll get there. All right, so whenever you got, let me just redraw an edge again. So inside a DAG, okay, so whenever you got, oh, thank you. Thank you so much. If you got U here, and also you got V here, so this one simply means U depends on, what I would say depends on here could be a little bit vague. How about this? This might be the most intuitive and better way to really interpret that. We're saying that U must occur before V. Before V. Okay? Think about the arrow really mean that. Occur before, must. Okay, it's a requirement. Okay, and then there's something called topological ordering. But let's give you one example about the DAG. Okay, I'm going to draw something here. Okay, I think since you guys are mostly from engineering, so I think that'll be relevant. Okay, let me draw the courses you're familiar with. Okay, let's put it here. Let's say we start with EECS3101, MATLAB. And also that one must happen before, for example, EECS1021, the introductory Java, right? So this one here will be EECS1021. And after that one there, you can go for 2030. Okay, I'll just put a number, 2030. And after 2030, you can go to 2101. 2101. And then after that, you can go to the current course, 3101. Let's add some additional prerequisites to make it a little bit more interesting. Okay, 3101. So there might be more than one prerequisite for a particular course. For example, for 2101, you also need to have taken, let's say 1019, the math course. 1019. And also, let's say before 3101, you also need to have taken 1090. Right? So this is just one example. Okay? So this graph over here is an example of DAG. First of all, we got directions. Number two, there's no cycle, obviously. Right? So it is, you satisfy the definition for a DAG. I can put another, well, also, it's not really necessary to have only a single connected component, for sure. Okay? For example, let's say, can you guys help me out? Give me two courses that depend on each other. That's not EECS. Yeah, okay, sounds good. Simple, okay. Do you remember the number? 1801? Okay, sounds good, okay. So here, these are also, these are also relevant. 1801, 1802, okay? Good. So now you can think about this is a DAG. We got two connected components, which is completely fine, okay? So now this is called DAG. And let me introduce another concept. It's called topological order. Topological order. Topological order is basically, we are trying to linearize the dependency. That's what we say. We are basically trying to sequentialize or linearize. Let's just sequentialize. So this graph over here is non-linear. But somehow, based on this, we're going to create some sequence from there. And the sequence you can create from a particular DAG may not be unique. So there might be several legitimate topological order. We are trying to sequentialize DAG. Okay, we're trying to sequentialize it. It's not unique. And whenever you're trying to sequentialize, it's not necessarily unique. Okay, I'll give you one example. Okay, let's say I have over here, let me start with 1801. It's like a sequence, okay? And then I got 1011, I got 1021, 1019, 2030, and also 1090, 2101, 3101, okay, almost there. Let's say somehow you take physics at the, in the beginning, don't like it, you want to take it at the end, 1802, right? That's the order, okay? Let's say if I give you some, like a sequence of vertices that exist in the graph, you can see we got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We got all the vertices. Now, how do we know this sequence over here is a legitimate topological order? Okay, let me do that informally, and then I will formulate it using predicate logic. Okay? Basically, you want to do the following. First of all, let's now try to index the sequence. Okay? So index, for simplicity, let's say we start the index from 1. You can start from 0 if you want to. Okay? So let's say this is index 1, index 2, 3, 4, 5, 6, 7, 8, 9. Of course, the smaller the index, the earlier the vertex appears in the sequence, that's for sure. All right? So now there's some exercise we want to do. We want to somehow reflect all the edges we have. Every time we have an edge, we got some origin and destination. Let's try to find them out in the sequence. Okay? So what we can do is, for example, let's say here, let's start with this edge over here. So that one there is really about 1011 to 1021, right here. Okay, we got another one. So let's get all these first. Okay, all these. So 1021, and also we got 1021 to 2030. They are not necessarily adjacent to each other in the sequence. And then from 2030 to 2101, right here. And also from 2101 to, oh, sorry, that one is adjacent, which is completely fine, to 3101, okay? So you can see we have covered 1, 2, 3, 4, 1, 2, 3, 4, 4 edges, right? Over here. Let me just maybe just make them orange so it's easier for you to see where they are. 2030, and also 2101, and also 3101. Okay, let's just focus on these. For any two vertices in the sequence that you claim to be topological order, any two vertices, if there is a direct edge between them, then so that means this must be a smaller index than this. All right, that's what we're saying. So that means we are respecting that 1011 must come before 1021. Also, we are respecting 1021 must come before 2030. But 1019 here doesn't really matter. It doesn't really violate the constraint about 1021 must come before 2030. We're still doing it. All right? And also 2030 must come before 2101. And also 2101 must come before 3101. Okay? Let's see another 3 arrows. And then we try to look at right here. So let's say 1019 and also 1090, right? 1019 must come before 2101. So you can think about 2101 is here and 1019 is over here. And we do respect that order because now if you put the green arrow here, right here, right? You can see there's a direct edge between these two vertices. And the index in the sequence is 4 and 7. 4 is less than 7, so we are still fine. All right? And similarly for 1090 and 3101. Okay, let's do that. So also for 1090 and also 3101 right here. Okay, so that one there we also have similar. Okay, so think about right here. All right? Okay, the final one, the physics. So we got this arrow here, the edge. Okay, so 1801 and also 1802. And that one, even though they're very far apart in the sequence, that's completely okay because we are still respecting the dependency. Okay, so that one there will go all the way from here to here. So this will be how you will actually judge, given some arbitrary sequence which cover all the vertices in the deck. Is it a legitimate topological order? That's how you judge. You want to make sure all the dependencies, all the individual edges in the deck, the orange, the green, the pink ones, they are properly reflected in the right order in the sequence. Follow so far? Okay, good. So now, there is a little formula that we put in the slides. Okay, let's now write it down. And so hopefully now this will make a little bit more sense. So let's say, take this one for example. You got this one. Let's say you got this one here and also this one here. So there is a direct edge between these two vertices in the deck. You can see the index is 1 and also 9. Right? You should really go from the smaller index to the larger index. It should always be the case. So now how do we specify that? Okay? It's going to say for every, so let me just make sure I follow the same syntax over here. Okay? So now we're going to use 2 dummy variables. For every I and j, I and j must be valid indices. Okay, they must be both. So you can think about 1 less than or equal to ij less than or equal to n here. So you can think about this is the number of vertices in the sequence, right? Just given. In this case, the n will just be 9. Okay? So after that, we're going to say also there is a direct edge between these two vertices. You can think about vertex I and vertex j is in the set of edges. So we're assuming that the DAG we have is basically a graph, which will be contain vertices and edges, right? We want to make sure this is one of the edges. For example, you can see this is one edge, right? This is the edge. If there's an edge between these two vertices, then that means I must be less than j, strictly less than. Cannot be the same, because we cannot have cycle, right? Given that there's a direct edge between these two vertices, their corresponding positions in the topological order must be this is strictly less than that. Okay. All right, it's a very quick introduction about defining terminology. Number one, you want to know what a DAG is, about direction and also node cycle. And then you want to make sure you compare DAG with the versus tree. And we talk about what really means to be a topological order given a DAG. Okay. Questions before we move on? Okay. So this is good. And then whenever you're saying given a DAG, you want to return some topological order. The process is saying you're doing a topological sort. I'll write this down explicitly. Okay. So given some input DAG, and then you want to return a topological order. The process saying you're doing a topological sort. The word here has sort, but we're not really like a sorting into ascending or descending order like what we did in heap sort or merge sort. Not really. We're trying to somehow sort according to dependencies. So the sort here is not really based on the values for individual vertices. We are sorting based on dependencies. So based on the dependency link, dependency links in the DAG. Okay? And the implementation for this is incredibly simple. If you know about how to do depth first search, we do know how to do it, right? We kind of did it in the assignment number 1 programmatically. We also did the tracing a lot in the lecture as well. Okay? So to implement this, you will just have to make some slight modification. Slight extension to depth first search. And I would like to point out right away, you might be asking, is it possible to really use the breadth first search to really do topological sort? Not in general. There might be some other algorithm existing trying to do some trick to modify breadth first search quite a bit, but the depth first search we're talking about is pretty much like how you understand about depth first search in the lecture. But if you just try to do the standard breadth first search to achieve topological sort, it's not possible. You'll run into some incorrections, which I'll show to you. If not today, definitely on Monday. Okay. A standard breadth first search cannot achieve this. Okay, it's important to know this point right away. Okay, breadth first search cannot. All right, and let's now take a look at the Java code for topological sort, and then I'll point out to you what's really there, and then we can work out the running time right away. What's the kind complexity? All right, it's actually quite easy to see, but we'll see. Okay, okay, let's now take a look. All right. So if you recall, when we did assignment number 2, in order for us to figure out the number of connected components, the way to do it is you have to keep running breadth-first search or depth-first search until all the nodes are visited, right? We're doing something exactly here, all right? So let's go over the structure. So when you define the topological sort algorithm, let's say we start with this, topological sort, okay? And the input is simply just a graph, okay? And you can think about the graph itself, maybe edge list, it might be adjacency matrix or adjacency list, depending on how you implement it. And the topological sort is just going to return some iterable of vertices. You can think about dynamically, it could be just an array list, right? Okay. And then we initialize some empty array list to begin with. And then we simply pass this particular list over here into potentially multiple topological sort we have to do. So you can think about each topological sort is only going to sort the corresponding connected components. Okay, I'll write it down. Think about each run. Each run only sorts vertices in some connected components. If you got multiple connected components, that means you may have to do sorting maybe multiple times. Okay? It's like if you really have to visit all the nodes in the graph, you may have to do the depth-first search or breadth-first search multiple times. Similar idea. Okay? So basically, you will see that we're going to go over all the vertices to see which one we want to start with. I'll give you a concrete example in just one moment. You're going to pick some vertex each time, and then if the vertex you're picking is not visited, so we are making some assumption. So we are making an assumption that for each vertex, we are marking the vertex itself to see that has been visited. Okay? Okay, so we got some assumption. So each vertex is marked as visited or not visited, or unvisited, just Boolean. If you somehow recall what we did in depth-first search, as soon as some vertex has been visited and also all the incident edges have been marked, we can pop it off from the stack, right? That's all we learned from the depth-first search. We'll revisit that very quickly when we trace. Right? All right, so eventually we're gonna return this order. You can think about this sub method here, we call it DFS and then topo. It's more like an extended version of the depth-first search. Each time we're just gonna extend or accumulate this particular array list until we can cover all the vertices from the graph. Okay? Let's now take a look at what individual topological sort is gonna do for each iteration. Okay? So that one there, let's now use. So this one here is gonna be this method here. Okay. Of course, it should be a void. It doesn't return anything. Okay. It's an iterative method. Okay. So again, we actually got the graph, and also we got some vertex that we pick to start with. Okay. You can think about this V here is unvisited to begin with. And also we got the order. So this will be the ultimate topological order that we want to return. Okay? So this is more like a topological order so far. Topological order so far. All right? So I'm not going to dive too much into detail like a line by line. So this one corresponds to exactly how we do depth-first search. I'll just highlight certain parts to help us figure out the running time, okay, the time complexity. Okay? Let's start by looking at the stack operation. Okay, I'm going to highlight in green. Okay, so you can see that we are just using. I'm just assuming that we actually got some stack class, and then we're using a linked list to implement a stack. Of course, you can use array list if you want to. That one doesn't matter. Okay, so let's look at all the stack operation first of all. Okay, you will see that we got. First of all, we create a new stack to be empty, right? And then we try to push the very first unvisited vertex into it, just some starting point. And then we are going, the outer loop depends on whether or not the stack is empty. You can think about, we'll keep adding vertices into the stack until there's nothing else to add. Okay? And also we can push here, and also we can pop right here. All right, so these are all the places where we try to manipulate the stack. Okay? So as we kind of do the tracing, we know that every vertex in the graph ultimately is going to be pushed into the stack and pop it only once. We never try to push the same vertex into the stack twice. So always just once, exactly, right? That's something you can definitely double check with the logic of the depth first search. So let's start with this one here, some observation. So just for right here, so we're going to say every vertex is pushed to and popped from the stack once, exactly once. So this will ensure we got exactly like a n, big over n, running time to actually get the all the vertices, into the stack and out of the stack. Okay, so that's one part. Another part is about incident edges. How many times are we visiting all the edges? So for each vertex we are visiting at the moment, we're going to go to the outgoing edges. Because it's directed, for example, here, we want to look at only the outgoing edges. If there's the incoming edges, we don't care. We want to branch out, basically, right? Just outgoing edges only. Okay. So about outgoing edges, and then here we're going to say that while we have more incident edges to really visit, we're going to keep going. So you basically visit all the edges that's incident on this particular vertex. Okay? So this part here is really about visit all incident edges once, outgoing specifically. Okay? And then notice that here, when the edge itself is going to lead us to some unvisited vertex, we call it discovery edge, right? That's from test number 1. Discovery edge, and then we're going to do something. We're going to push that to the stack. Okay? So you can think about each edge is marked only once. Of course, the more detail will be, you can mark it either as discovery or back edge. We don't really need that detail over here. You just got to remember, whenever you're leading the incident edge to some unvisited vertex, you got to do something. In this case, you're going to push the vertex into the stack, like how we did earlier. All right. So now, given what we have said about we're going to push and pop each vertex into the stack only once, and also each edge is going to be marked only once. So overall, the running time for a topological sort is just going to be like a depth first search. So the runtime is just going to be big O of, you can think about the number of vertices plus the number of edges. Okay, that'll be overall running time. Or you can say the big O of n plus n. Okay. So this also tells us, remember the graph question that we spoke about earlier, right? Like a various graph question you can answer using depth first search or breadth first search. Very likely, if the question itself is a very simple adaptation from DFS or BFS, the running time most likely should be around n plus n. That should be in general the case, okay? If you don't add too much complexity to it, okay? Okay, one more detail to mention, okay, right here. If you look at this line here, this is also critical, okay? Because the order is something we want to ultimately actually return as the topological order. So now, you can see that we are saying at first, okay? I'm going to show to you once we get there, right? This at first ensures, okay? This is also some observation you see on the slides. This will make sure the topological order that we're going to return is the reverse of vertices backtracking. Backtracking in the sense that we're popping that off from the stack, right? We also talked about backtracking earlier, when we talk about backward search. Beg your pardon. The reverse of the backtracking, all right? But we'll see an example to really see exactly how this works. Okay? So the algorithm itself is actually not complicated. You just have to know how to use the depth first search, and then at the same time, you want to maintain some array or maybe array list, and then you want to keep accumulating that particular thing list until all the vertices are done, actually visited. Okay. Any questions so far? Okay, all good? Okay. Okay, I think it might be nice for us to take a short break. We're now almost halfway. So after the break, we're going to do just examples. We got 3 examples here. We'll see how many we can do. Okay. Okay, let's now take a short break and then we'll take attendance. All right, so let's now take a look at example. I got 3 of them. I think I got example 1, 2, and also 3. I would suggest I will at least talk about 1 and also 3. 2 is quite similar to number 1, just slightly more complicated, but you do have the solution also on the slide. Let's do number 1, make sure you know how it works, and then once you get an intuition, we can solve some very interesting problem over here using topological sort. Okay. And then, if time permits, I'm going to talk about why you cannot really use breadth first search for topological sort. Just give you some counter example. And that should be enough for today. Okay? Let's start with this. Okay? Number 1, can you justify if it's a DAG? For example, I give you an exam question. I ask, given this graph here, explain if it's a DAG. How would you say? Yeah, go ahead.
There's no cycle.
Okay, there's no cycle. Okay, that's good. That's only one component, right? Yeah. And what about the other one? Directed, exactly, right? Simple question, right? Well, simple answer. Good, very good. All right. So now here's the thing. When you do that visually, I can say, if you want to do a topological sort, you may want to somehow go to the leftmost vertex to start with. Basically, the one that's without any incoming. With the minimum incoming edges, for example, this one with no incoming edge. That means that should be, maybe that can give you the minimum number of DFS to really run. Because once you start with this, for example, you go for A, you can always you can reach out to the most number of vertices, most likely. So you're basically done with just one iteration, right? Remember the while loop over here? The number of iterations you have to run over here depends on which vertex you will pick each time. But when you are running this as a program, you have no control unless you do some little bit of checking, but that's not worth doing. You might just add some complexity to your program. So let me try that to say, let's pick maybe some vertices that will give you multiple times of running the topological sort, just to see, okay? So let's say this. Let's start with something very simple, okay? Let's say this. Iteration 1. Iteration number 1. So what we have is we got DFS topological sort. And if you recall, that one there is going to take the graph. Okay, let's omit this input because we know the graph is here. Okay, it's going to take some vertex that's unvisited and also the topological order we're going to return ultimately. All right. So let's say that's going to take let's say E. Okay, let's say we start with E. And then the initial order is simply empty, let's say. All right, so that means we're going to do a depth first search from E. As you can see, this one here is not going to reach to all the vertices, which is okay. All right. And let's also make the assumption that we're going to visit the incident edges by following alphabetic order. Okay, let's have that usual assumption. So let's say we assume the incident edges visited in alphabetic order. Okay, that should make the assumption. Okay, so we start with E right here. So the first we should visit will be here, D. Right? Let's number that. Right? So this will be the first one. Okay, so let's use a stack at the same time. Okay, remember we got push and pop, right? Why don't we do that just systematically? So we got push and pop. Okay, since we start with E, we're going to push E to the stack. At the same time, let me also maintain a stack right here. Okay, we push E. And then we're going to push D. Okay, so now D over here has no further incident edges. So that one will be considered as visited. All right, so that one there, we're going to pop it off from the stack. Okay, you can think about at this point, I'm just going to call it that, right? So you can think about this one is completely visited. Okay, and then we're going to backtrack. So this, you can think about D here is the first one to be popped. As soon as you pop the vertex from the stack, at the same time, let me refer you to it. As soon as you try to pop it off, make sure you add it to the order. Okay, so that means over here, we're going to have basically, okay, as soon as we try to pop it, so you can think about D is right here. Only one vertex in the sequence, okay, in the array list. And once D is popped off, so now we got E. E is now going to another incident edge. So that one there is actually going to right here, okay? So that will be number 2. So we're going to push F right here, okay? So once we get to F right here, you can see it has no further incident edges, so this will be considered as visited. All right, so this one here, we're going to pop it off. Of course, we push it first, and then now we're going to pop it, right? And then we're going to put F right here, at first, not at last, all right? So F should also be popped. So that means now the top of the stack is just E. And E, as you can see, both incident edges have been marked. So now we can backtrack. Basically, E is now also gone. We can also remove it from the stack. This will be popped. And now we got E. Okay? So after the very first iteration, we have already visited these 3 vertices. Okay, these 3. And then the order we have got so far is over here. Okay, so this is the order from here. And notice that any future DFS topo we have to do, we're going to accumulate this particular list. Right? That's why it's passed as an argument to the method. Okay, so far? Okay, let's see. Another one. Why don't we try one more? Of course, if you choose A as the next one to really visit, you're basically done because that can reach out to all the vertices, right? Why don't we do that? Okay, let's give it a try. Okay, let's try another one that's more fun. How about we do this one here? Okay, let's say the next one you're gonna do, let's say start with B. All right, this one here. Yeah, I do want to show you the first example. You can have multiple iterations, so you really see. You don't necessarily be able to visit everything at one go. Okay, so iteration number 2. Iteration number 2. So that one there is going to be another run of the DFS topo, and we're going to start with B. And now be careful. The list you're taking now is no longer empty. You accumulate it from the previous iteration. It's going to be E, F, and D. Also, one thing to note. As far as dependency is concerned, E, of course, must go first. Whether we should go for F or D or DF, it doesn't really matter. as far as dependency is concerned. The reason we got FD simply because we assume we're going to visit in alphabetic order, right? But they're both legitimate topological order. Okay? So I would say in the exam, I might give you some explicit assumption about maybe we should really revisit the incident edges in the alphabetic order or a particular order. In that case, it's easier for us to see what's the unique order you will have. But if I don't put that restriction, you can do whichever order you like. Okay. Good. Okay. Again, the most important thing for you to remember to note is this one here is not empty to start with anymore. All right. And let's now also do a local table here for the push and pop. Okay. Okay. So we got push, and also we got pop, right? Also we got a stack here. That should be big enough. Okay. So let's say we go for B. B is pushed. Okay, so B got 2 incident edges. Alphabetic order, we're going to go for this one here, right? Go for C first. So what we do is we're going to have right here, right? Going to go this way here, and then we're going to go for C. So C should be pushed. So C should be pushed right here. And now for C here, there's only one incident edge for C. But that one, if you check it, is leading to something that's already visited, right? So nothing else for us to do. But I can still mark the edge. So this will be back edge, for example, right? Because this is side, yeah, there's a back edge. All right, so once this is done, so as far as C is concerned, so now we have handled all the incident edges, okay? So now we can simply mark this as visited. So C is now going to be removed from the stack. Okay, so C is popped off first. Okay, so that would mean in the sequence, we used to get E, F, and D. So now since we just pop off C, right? So get F first, C here, right? And then after that, the top of the stack is now B. So for B here, this is already visited, it's already marked. So only this one here, but it's also leading to some visited node. So we don't need to do anything, okay? So that one there is also here. So now B is also considered as visited, okay? So we also try to remove B. And make sure you add first right here. So now after iteration number 2, we actually got this order, B, C, E, F, D. Okay, B, C, and then E, F, D. Okay, you can also double check about how we judge to see whether some order is really a legitimate topological order. That's something we spoke about before the break, right? You can double check. Okay. Right, we haven't really visited all the nodes just yet. Right, so we're going to go for iteration number 3. Okay, final one. But that one, as you can see, is going to be very easy. So let's now go for the final iteration number 3. So now in this case, we're going to do the DFS topo. Okay, now this time, the only thing that's unvisited is A. So we're going to start with A, and then the sequence we're going to start with will be B, C, E, F, D. Okay, right here. And then, so we start with that. But this one here should be very trivial because now we have already done all the work. So this A here, well, let's still do it. So you can think about we got a stack over here, push and pop. We got push, and then we got pop. So we first of all push A, there. And then, of course, A has got all the incident edges leading to nodes already visited. Nothing else for us to do, right? So we're going to pop it. So we're going to pop it off. You can think about the stack, of course. A here, pop it off, okay? So what we do is we're going to add A to the first. So it's going to be, so think about what's here. I'll try to be careful about the color. So E, F, D from the first iteration, and also we got BC. And right now we add first A. Okay? So this will be the sequence. Okay, so think about this is the ultimate topological order to return. Because, of course, at the same time, A is also considered as visited. Questions about this? I hope that's clear. So you got to make sure whenever you want to trace for topological sort, what you should do is you got to keep picking unvisited nodes from the graph. Of course, in the exam, if I didn't tell you which one to pick, you should really try to pick the one that can reach out to the most, and then try to go from there, right? And sometimes even though you pick the node that can reach out to the most, you still maybe have to pick the second one to really make sure you visit all the nodes. But if I give you some particular order of the vertices to pick, you have to also work accordingly, right? It really depends, okay? So for this particular example here, it's very important to realize we're basically doing the order of pick E, and then pick B, and also pick A, right? That's a particular order, okay? Questions? Everybody's good? Okay. Let's now look at some interesting example, okay? Okay, example number 2, it's just slightly larger graph, right? I just kind of, still like an A, B, C, D, E, etc. I just kind of put some real life example in context, right? So for example, you must do exercise or breakfast before you go to work. Both of them must be done before you can do this one here, and etc. It's just a little bit different topology to explore, okay? Exercise for you, you can think about how many possible topological order you might be able to devise. Then try to experiment that with that a little bit by picking maybe different unvisited vertex to start with, and etc. Okay, I'll leave that to you. I do suggest some different topological order in the slides. Okay, I'll leave that to you. Okay, I think we got about 20 minutes. I think at least we can talk about this example thoroughly. Okay, talk about this one here. Okay, so this one here is more like a one problem that topological sort can just solve for you. Okay, let's say the following. Let's say I'm trying to do some specification. So think about, I'll explain the notation to you, and then you can tell me how we can go about it. Let's say what we have over here is the specification of transactional updates. So the way I specify is by not really using variable assignments. I'm not using it. I'm just using mathematics. Okay, I got conjunction here. I got conjunction here. Conjunction here. Okay, you can think about the update are specified as constraints, not variable assignments. That's something we would like to produce eventually, but not here. Okay. Think about this one here is the input, okay? And let's explain. What's really the prime here really means, right? Think about the update I'm specifying is more like a transition, okay? So think about what we're having is here. So let's say over here. The way to understand it is, so the transaction update itself is more like a transition, okay? So this will be the transactional updates. And this is before the updates, and this is after the updates. And if you recall what we talked about in the client-supply relationship in the very beginning of the class, we talked about pre-state and post-state, right? It's kind of relevant here, okay? So this is after. So this is the pre-states. And this one here is the post states. Okay. And we have 4 variables. The convention is every time you're specifying constraint, right? on the left-hand side, the convention is on the left-hand side, we simply put the post-state value. Okay? So these are the post-states value of variable. Okay? So we got 4 variables in total. Okay? So we got A, B, C, D. So we got A, B, C, and D. If we want to refer to the variable's value before the updates, we use A, B, C, D without the prime. But if you want to refer to the variable's value after the updates, you're going to say A prime, B prime, C prime, and D prime. Okay, so conceptually, you can think about there are 2 copies for each variable, the pre-state copy and the post-state copy, right? And the specification over there is trying to specify the relationship between the pre and post states. What we want to really do is, based on this specification, we want to schedule sequentially the variable assignments to achieve what is being specified. Interesting problem to solve. Okay? So that's what I put in the task over here. We want to sequentialize the specified transaction update. For example, this one here, I'll give you a little bit hints. When I say C prime, which will be the value after the updates, should be equal to the B prime over here minus A prime plus the D over here. Okay? What that really indicates is, can I try to calculate C prime before I calculate B prime? Not really, right? So that one tells you, before I can ever compute C prime, I should really suspend it. I should really calculate B prime first. So anything you talk about something should happen before something, you got dependency. And you got a potential of having a DAG. All right? I'll pause just for 1 minute. What you want to think about is, now, given that there's certain dependency, okay, I'll write it down. So I think that'll be fair hints to you, because this might be something very new to you. Okay? So think about this one here. If you look at C prime here, and also B prime, I'll put a star here. Okay? So when I got C prime equals B prime, ... that tells me that B prime should be computed first. Before C prime. Right? That's a very important insight. And of course, there are so many dependency links we can draw or we can infer from this specification over here, amount A, B, C, D. I'll pause for 1 minute. Are you somehow able to draw the corresponding DAG based on the dependency here? Okay, think about it, okay? The first question you may want to think about, okay, again, just want to give you more hints. Let's say just based on C prime and B prime, should I draw it something like C prime, B prime? Or should I draw something like B prime, C prime? You got to make a decision. Okay, second one, okay. Just leave their thoughts there, okay? Because if you draw it, for example, if you choose a wrong path, like what I did earlier this morning, you will just get yourself very confused, okay? So think about it. Okay, this example here very nice because you get something that doesn't really give you any hints about what you should do. But you want to think, since there's some dependency among the various artifacts, so you know that you might just be able to draw some DAG out of it. And then after you have a DAG, you know that you can do topological sort. All right, just pause for 30 more seconds and then we'll do it, okay? Do you guys agree? 1 or 2? 2? Okay. So that means B prime should be computed before C prime should be computed. Awesome. All right. Okay, I'm going to wipe it out. Okay. Questions?
Yeah. When I'm doing this, like, let's say for example, I am doing for going to B prime line. I I still have a reference to the original D as well.
Oh, that one, okay, that's very good. So that one there is, it turns out it's not the issue.
Okay.
The prime is really the issue, yeah.
So like after I calculate that line, I have D prime and I also still have my original D, right?
You can assume, yes,
Okay.
yeah. That's a very good question, yeah, very nice. Yes, I agree. Yeah, very good. Yeah, so of course there's a certain assumption, right? So there's a bit more implementation detail. So let's assume. Assume that we have, let's say there's some value called old D is assigned to D. And also, I'll get there a little bit later. Once we get to that particular part, I'll fill it out. But I know exactly what you mean. Okay, let's now take a look. All right, so let's now build a deck together. Okay, let me just look at my notes just to be sure. Okay, good. Okay. Let's now start with, first of all, the first line. So we can see that C prime over here, before that, B prime and A prime should be computed, right, based on that, right? So let's draw that dependency right away. So if so that means B prime must come before C prime. And also A prime must come before C prime. Okay, you can think about this part here really correspond to the yellow. Okay? Are we okay with this? Good. Okay, the next one. Of course, it doesn't really matter which one doesn't matter the order we are running around the lines, right? Doesn't matter. You're going to build the same graph anyway. So the next one, let's see, we got B prime, A prime, and D prime. So that means A prime and D prime should really be calculated before B prime. Okay? So now if I go for A prime, that should go before D prime. A prime should go before B prime. Like that. Okay? And also D prime should go before B prime. Okay, good. And these two are the green. Okay, gradually. All right, and then now for D prime itself, because it only depends on the O value, we don't need to worry. It's really the prime value that we kind of worry. We'll see why. Okay, and here no dependency should be reflected. And finally, you can see A prime here also depends on D prime. Right? So what we do is you can see A prime here and also D prime. So D prime must come before A prime. So what I will do is, so D prime must come before A prime. Right here. All right, you can now verify right away. Is it a DAG? It is actually, right? There's no cycle, right? Good, okay, it's a DAG that we have built. You can see we take this guy here and then we extract a DAG out of it. All right. So this is the DAG that we have. All right. And then we're going to do a topological sort on that. Okay. So we're going to do a topological sort. And of course, again, it depends on which vertex you will pick to start a topological sort for the first time, right? Let me say I'm lucky. I happen to choose D prime to start. Question?
Well, we don't need to write up the A and C, but and D, like the non-prime, but why?
Say it again. I don't quite catch you.
Like the non-prime value, why?
It turned out we don't need to worry. We only need to worry about prime. It's kind of the assumption that your fellow student was asking. I'll write it down in just one moment. Okay? So you might be wondering about, what about the pre-state value? It turns out we don't need to worry about just yet. Okay, we'll get there. Okay, yeah. Okay, let's do a topological sort. Let's say I happen to choose So we got DFS, topological sort, and then we start with D prime. And then we got empty list to start with, right? Okay, so now we're going to, again, have a stack right here. Okay, and then we got push and pop, right? I know it's simple, but let's just still be systematic. Okay, so we got push, and then we got pop. All right, so we start with D prime. And you can see D prime can either go to A prime or B prime, right? Let's say we go for alphabetic order. So we go to A prime, okay? And then we go for A prime, A prime. From A prime, we go to B prime. And from B prime, we go to C prime. Okay, so D, A, B, and then C, okay? So once we go to C prime over here, it has no outgoing edges. So that one should be considered as visited, right? So that one should pop off. So C prime should go away. First pop, okay? And then the order itself is going to add first, so C prime should be here, right? And now the top of the stack should be B prime. For B prime over here, it only got to C prime, but C prime has been already popped off. It's being visited already, right? So there's nothing for us to do. So we're going to also pop B prime off the stack. Okay? And then we go to A prime. A prime over here, we basically can either go to B prime or C prime, but both of them have been popped off, which means they have been visited already. So nothing else for us to do, so we're going to pop it off. A prime should go away over here. Now the top of the stack should be D prime. Similarly, it goes to either B prime or A prime. But both of them have been also removed from the stack, right? So pop it off, D prime. So the order is going to go like this. C prime, B prime, A prime, and D prime, okay? So this will be the topological order, okay? Okay, so this would be topological order. Okay, so now how do we use this result? So this is saying we should really try to compute the value for D prime, followed by A prime, followed by B prime, followed by C prime. That's what we should do, right? And now let's talk about also the assumption. Okay, I'm going to write it in the same place. Okay. So let me save space just right here. Okay, let me just put this away. Oh, sorry. Let me just write it down here. So the start there, when I say C prime equals B prime, that means B prime should be computed before C prime. Okay, I want to save some space right here. Okay, right here. So how do we use the ultimate result right here? Okay, right here. So we assume that before we even try to look at the computation for the prime value, let's save the O value to some additional variables, temporary. Okay, so since we got A, B, C, D, you can think about we got, let's say old A is assigned A. Old B is assigned B. Old C is assigned C. And old D is assigned D. So later on, even if A, B, C, D might be overwritten, we can use the O value. They are stored. Right? You can think about this part here is somehow outside the scope for the topological sort, but it's something we want to use to as part of the sequentialization, okay, for the updates. Okay. So after that, we're going to go for the topological order, which we know is going to be this. So we're going to go for D prime, A prime, B prime, and C prime. So D prime is going to be turned into some variable assignments, and also A, and also B, and also C. And notice the following. The final outcome is going to be variable assignments, okay, colon equal. And the equality here is more like a constraint, like a Boolean constraint. So they're totally different, right? Just don't get confused. So now I'm going to following DABC, DABC. So for D over here, it's going to be A plus C plus 5. Whenever I see any unprimed version, I can use the O value, OA and OC plus 5, right? So here I can say old A plus old C plus 5. So this one here should be the first one calculated. And then when I go to A prime over here, it's going to be A here, which will be OA. Now plus, when I see D prime, I can just say D. Guarantee the D over here is really referring to the post-state value that's been already overwritten, because now we already got sequential composition, right? We got sequentialized updates. So this D here is really the D prime that has been already updated. Okay? Okay, continue. And then for B prime here, it should be A prime and D prime. That one there will be simple. We can simply say A prime multiplied by D. So you can think about the A here is referring to the A just happened, guarantee, right? It's a topological order, okay? And also the D here is also referred to the D here, all right? Finally, for C, it's going to be B, A, and also old D. It's going to be B minus A plus old D. And you can see that guarantee the B here has been already done. A here also has been done. If you follow this order here, it's going to be without any inconsistency. Okay? So what we have turned out to be is, for this kind of constraint, like a parallel updates, we try to sequentialize it into variable assignments. And it's a very nice way to really build a deck and also use topological sort. Okay? It's one very practical application. You might find a use at some point. Okay? Any questions? So the topological sort itself is pretty straightforward to really do. You just have to know how you can build a sequence, the topological order, from multiple calls to the DFS. Just make sure you accumulate the order properly. And now, what's going to be challenging is, maybe in the exam, I might give you a slightly different problem. And then you have to know that you have to use topological sort. How do you tell in general? If the problem itself might indicate certain dependency among the vertices, then topological sort and deck might be a good candidates for your solution. Right? Just keep that in mind, right? That's how I would see it as well. All right, guys, any questions? Yes?
Is there any way to represent like sort of a optional condition? Like right now C requires both B prime and A prime to be done. Is there any way that we could represent like C prime requires either B or A?
That's a good question here. It's definitely, let me try to see if I can come up with something, and then I can come back here. Okay? So Josh's question is it possible, okay, or just say question here. Is it possible to have, for example, maybe before a particular variable, I need to do two things over here? That's what you're asking. I'm pretty sure it's possible.
Well, more like either one of them will satisfy. Like, does it need both?
Oh, that's what you meant, right? No, I don't think so. Because the way you kind of put the edges, right? If you have one node with the two incoming edges, that means both must be happening before that one can happen, right? There's no optional. Yeah, okay, that's what you meant. Okay, good. Any more questions? Okay, so I think I only got one more thing that I want to talk about for topological sort, which will take me just 2 minutes or so. That's something you guys can think about. I'll give you the page, okay? So now, we want to just understand that in general, give me 1 minute, okay? In general, you cannot simply apply the breadth search, which will divide the graph into levels, as we said, we kind of learned from test number 2. Take this graph over here, visualize it, and then try to apply, number 1, the topological sort, like using depth search, versus using breadth search. are you going to get the same order from there? All right, so that's something you want to think about, but I'm going to go over that as well. A very simple one, the simplest content example we can look at to know that you cannot use breadth first search in general for topological sort. It has to be depth first search. Okay. All right, guys, thank you. And then I will see you guys maybe Monday for the last class. I'll confirm with you about the tutorial, what is you did any exercise to do. Okay. Otherwise, I might just assign something for you to do. Okay. Thank you.